Hello back. We're going to talk now about molecular orbitals of conjugated molecules. You may recall from your general chemistry days that when you bring an atom close enough together to a second atom, and provided that the atom in question contains p orbitals, the p orbitals can overlap with each other. They could form sigma bonds, but right now we're gonna completely pay attention to just the pi bonds because they're the ones that are most crucial for the chemical reactivity of conjugated molecules. So if you think about two p orbitals that are parallel to each other, side to side in essence, and you bring them together, there's two ways to make this happen. One way to make it happen is to have the two orbitals in phase with each other, meaning that when you look at it from side to side, the shading is the same on the left and the right portion of the molecule, and that's true for the top and bottom sections of the p orbital. This is what we will call a bonding pi bond, and at the same time, when the two p orbitals come in contact with each other, statistically, they also have the chance of meeting each other out of phase, so that they end up forming an anti-bonding pi bond, which is higher in energy compared to the individual atomic p orbitals. Now, you may remember that when you construct these molecular orbital diagrams, the electrons from the atomic orbitals are distributed onto the lower energy molecular orbitals first, and until you fill them all up, you don't go on to the next molecular orbital. So being the case that, for this example, for ethylene we only have two pi electrons. That's the reason why you see only two electrons in this diagram, because we're only considering the pi electrons, right? Not the sigma, just the pi, and there's only two pi electrons in this double bond. Those two electrons will go into the pi orbital, which happens to be bonding. And that's a great situation, because what this is telling you now is that by actually having the two atoms overlap with each other, in essence create a bond, you are generating a much more stable situation by having electrons occupying lower energy molecular orbitals. And also, you may remember this from 201 or whatever general chemistry class you may have taken. The orbital where you have the last set of electrons present is regarded as the highest occupied molecular orbital, or the HOMO orbital, whereas the next orbital where there is no electrons is referred to as the lowest unoccupied molecular orbital, or the LUMO for short. All right, so we talked about the lowering of the energy as a result of electrons occupying the bonding orbital is the reason why these atoms are forming the bond in the first place. And we're going to be focusing a lot on the HOMO and LUMO orbitals, because as you'll see throughout this lecture, it is the interaction of those two frontier orbitals that explains all the chemistry that we're going to be seeing with conjugated systems. All right, now, when we get to slightly more, slightly bigger molecules, and this time a molecule that is in fact conjugated, such as 1,3 butadiene. Now, this is presenting the molecule in a trans-like configuration. It's not exactly trans because you don't have more than one substituent on either of the alkene, segments, but it has that kind of trans configuration in regards to the single bond. So we refer to this as the S-trans form of the molecule. And if we go back to this idea of the molecular orbitals, you don't have to start from scratch, because if you kind of think about it, butadiene is technically two ethylene units brought together, making a new bond in between the two central atoms. So you could literally take the molecular orbital of ethylene, which has the bonding pi orbital and the anti-bonding pi orbital, right? And you just have two of them, kind of like what we did for the two individual carbons. And remember, each pi bond is two electrons, so we have the two electrons in the bonding orbital, two electrons in that bonding orbital. But when we bring them together, until this carbon on the right side of the first ethylene and the carbon on the left side of the second ethylene molecules, until they come together and they overlap, you have the same situation happening, namely that when you form that new bond, you have two ways that this can happen. The two bonding pi orbitals can overlap constructively with each other, in essence, be in phase with each other, meaning that all the orbitals are of the same phase, or alternatively, the pi bond on the left can meet with the pi bond on the right out of phase with each other. So what that will mean is that you will have a pi orbital which has the two lobes on top shaded for the first two, but then the shaded lobes are on the bottom portion on the last two, right? So that will be an out of phase interaction from the point of view of the middle carbons. And you probably already noticed this, that I'm starting to populate the electrons, right? We have two electrons right here and two electrons right there, so we can populate the lowest level by two electrons, but then we can also populate this other level with additional two electrons from the second pi system. And once we do that, we have accounted for all the pi electrons in the molecule. So this particular molecular orbital is the HOMO orbital of the entire molecule. Now, if you consider the same idea for the antibonding orbitals, the same thing can happen. You can bring the two antibonding orbitals such that the middle carbons are in phase with each other. And as you can see right here, the middle carbons, are in phase with each other, right? That doesn't mean that we're changing the picture for the leftmost or the rightmost part of the molecule. That it still has to be antibonding because it's deriving from the antibonding pi orbital of ethylene. But the middle section is the one that is bonding. And this is the orbital, the first orbital where there is no electron. So this is technically the LUMO orbital of the molecule. And then to complete the full picture, you basically bring the two pi bonds out of phase with each other. So now if you look at the middle carbons, you'll notice that they are alternating in shading, meaning that they are destructively interfering each other. That will be your fully anti-bonding situation. And then if you want to be even more technical, if you look carefully, you realize that as you go from left to right, the alternation happens every single step of the way. So this is the worst out of the bunch. This is the most anti-bonding out of all the orbitals. But, as you can see, we only had 4 pi electrons to deal with because we only have 2 double bonds. So we never even get to the point where we're filling up those orbitals. But, it will be important to pay attention that the HOMO and the LUMO are these 2 types of orbitals. Notice that on one end, for the HOMO orbital, the lobe that's shaded is on top, whereas on the other end of the molecule, the shaded lobe is below. If you go to the LUMO, notice that the shaded orbital on the left side is above, and so is the shaded orbital on the right side of the molecule. This type of symmetrical kind of back and forth is going to play a big role in the explanations, and I'm kind of like really bumping it up, a lot, so hopefully you're getting the idea that this is important to take notice of how these orbitals look like, because in the next video we'll get into all of that. All right, now the second thing I want to highlight too is that if you consider the energy separation for the molecular orbital of ethylene, when you look at the separation of the HOMO of ethylene to the LUMO of ethylene, you have a certain range that it takes energy-wise to reach the LUMO orbital from the HOMO orbital. Another way to put it is that if we were to excite an electron from the HOMO orbital, you will have to put in this much energy for it to reach the LUMO, which is the next available orbital. But if we do the same analysis for the conjugated diene molecule, because of the way that the molecular orbital has to be constructed, the HOMO-LUMO gap is actually a lot smaller. So it takes less energy to make that promotion happen. So in essence, what we're seeing right here is that for the conjugated alkene, one, the energy gap is smaller than what we have for just the unconjugated system. But also, if you look carefully, you realize that the HOMO orbital of the conjugated alkene is higher in energy than the HOMO orbital of the unconjugated one. And moreover, if you look at the LUMO orbital of the unconjugated alkene is higher in energy than the LUMO orbital of the conjugated one. So what this basically means is that no matter whether the conjugated diene is acting as a nucleophile, a base, an electrophile, or an acid, it is more reactive than the unconjugated alkene. However, because you are full, actually putting electrons into orbitals that are lowering energy than the baseline orbitals of just the unconjugated alkene, they're still more stable than non-conjugated alkenes, but at the same time they're more reactive. And this is something you can only explain by looking at the molecular orbital. Otherwise, it's a very confusing type of thing to address. But yes, conjugated alkenes are more reactive, and they're also more stable, which seems to be like an oxymoron. But all the parts to that sentence that seems to be out of whack with itself can be explained by simply looking at the molecular orbital. And the last thing I'll highlight, kind of going back to the orbitals right here, is that as you go from the lowest molecular orbital energy-wise to the highest one, notice that you have an increase in the number of sections where the shading of the orbital changes. You go from having no changes whatsoever or no nodes to having one node where the change does happen, to having two nodes where there's two sections where the change happens, and then having three nodes for basically having changes happening every single time throughout all the conjugated carbons. All right. So in the next video, I'm going to tell you a little bit about butadiene, the transition between S trans and S cis. But yes, I think we're in a good position to stop because we talked about all the orbitals, and yeah, that's where we'll basically stop this video. So I will see you in the next one.